Hello students, I am Saroj, PGT Physics in Triveni Memorial Senior Secondary School, Barai Road. I am going to teach you chapter number 5, Magnetism and Matter. In this particular chapter, the current syllabus as on the screen you can see is according to 2021 syllabus. From there, properties of magnetic material have been removed. So I am going to discuss about the magnetic field lines and their properties. Second topic, current loop as a magnetic dipole and its magnetic dipole moment. And the next is magnetic dipole moment of an electron in a fixed orbit. Then bar magnet as equivalent solenoid. And the last topic is the earth magnetic field and magnetic elements. So this is the current syllabus, and I am going to discuss the 2021 syllabus only. So in the next slide I am going to discuss about the basic introduction to the chapter. So first of all, as we can see the term as magnetism. So what do you mean by the magnetism? So as on the screen you can see the definition: the property by which magnetic materials are capable of attracting the metals is called magnetism. That means any material which possesses the magnetic property, these are going to be attracted by the magnet. So in the next diagram I will show you. In this particular diagram, as you can see that there are the magnetic materials which are spreaded near to the bar magnet, and exactly at the center we have kept the bar magnet, and near from that the iron pieces or small magnetic material particles have been attracted by the bar magnet. And here as you can see small patterns of the magnetic field lines that we are going to discuss later on. And you can see that the magnetic material is attracted more at the south pole and the north pole area, and it is attracted less towards the longitudinal side. So now the next term is magnet. Now what do you mean by the magnet? So magnet is nothing but the material which possesses both attractive and directed properties is called magnet. For example, iron, nickel, cobalt, etc. used to show the property of attraction, and they are capable of attracting the various materials towards them. So generally the bar magnet have been made by the ferromagnetic material. Now the next one is natural magnet. So what are the natural magnets? Natural magnets are the magnets which are basically present in the nature. These are weakly magnetized, or you can say feebly magnetized. That means their magnetic property is weak. Now for example, iron ore, magnetite and lodestone, etc. These are generally present in the core of the earth only. Next one is the artificial magnet. As we know that artificial is anything that have been made by the human only. So as compared to natural magnets, these are fabricated by the human. These are the human made magnets, and these are strongly magnetized, as we have various phenomena by which we can make it strongly magnetized. We can increase its magnetic field strength. For example, the bar magnet and horseshoe magnet, etc. Now so the artificial magnet can be demagnetized by increasing the temperature across the bar magnet, or you can say by the hammering process. Now in the next slide I am going to discuss about the properties of the bar magnet. So the first property is the directive property. Directive property says that whenever a freely suspended magnet always align itself into the south and north direction of the geographical south and north. So over here we can talk about with respect to the diagram only. So you see the diagram over here, there is a diagram in which we have a freely suspended bar magnet, as you can see in this particular part, and there is a south and north direction denoted in the same axis. So the north is going to align with the north, and the south is going to align with the geographical south. So over here this property says that whenever the bar magnet have been freely suspended, its north pole is going to align with the geographical north, and its south pole is going to align with the geographical south. Now in the next part, the second property is, like magnetic poles repel each other and unlike magnetic poles attract each other. Over here, this is you can say a general case. In our childhood also we have experienced this thing. Over there we have we have the two magnets, then whenever we have just keeping the n closer to each other or ss closer to each other, these are never ever attracted to each other. There are always a force, there is always a distance which always lies between the two, which do not make them to come and join together. That particular force is nothing but the force of repulsion between the two like poles. Similarly, whenever we keep n and s closer, they sharply just come together and join together. So this is the property, that is force of attraction between the north and south pole. So unlike poles attract each other and like poles repel each other. Now in the very next case, there is a magnetic poles exist in pair always. That means monopole do not exist in the magnetism. And over here the diagram that I have taken from the Google site, and reference have been given at the you can say denominator part. So this diagram shows you that whenever there is a bar magnet which is going to break down into the multiple pieces, that you can see in the first case it have been divided into two equal parts. So these two equal parts again have the south and north together, south and north together. That means whenever the bar magnet have been going to break in multiple pieces, automatically at the one end there will be the south pole which is going to generate, and at the another you can say side, the second pole is going to generate automatically, which will be the north pole. So in this particular diagram we can see that the monopole do not exist in case of the magnetism. Now in the very next case I am going to discuss about the magnetic field. So what do you mean by the magnetic field? So by the definition, first of all we want to see, then we are going to study it with respect to the diagram. So the space around the magnet in which the magnetic force will be experienced by the magnetic material is called magnetic field. That means the space around the bar magnet in which the magnetic force can be experienced by any material, due to which it will be attracted towards the pole or towards the magnet. That particular force, that particular space in which that force is present will be called as the magnetic field. Now the next case is the uniform magnetic field. Now what do you mean by the uniform magnetic field? Uniform magnetic field is the field in which at a particular point there will be the same magnitude and the same direction of the magnetic field at that point for all the, you can say, magnetic field lines. So I am going to show you it with respect to the diagram only. So first of all I am going to you can say read out the definition first for you. So if the magnetic field has the same magnitude and direction at all points in a particular region, it is said to be uniform magnetic field. So now over here you can see that this is the pattern that generally in terms of continuous line we used to show the magnetic field lines, and if these are straight, these are parallel to each other, then these are going to have the same direction as these are parallel to each other, you can see, and these are also going to have the same strength at a fixed point. Now next one is, you can see on the screen, is the cross. This particular cross also shows you the uniform magnetic field, which is showing the inward direction to the plane of the paper. Now in the very next case we are going to see the dot. It is also a uniform magnetic field, but it shows the direction of the magnetic field which comes outward vertically or perpendicularly coming outward to the plane of the paper. Now these are the, you can say, nomenclature for the first figure, uniform field on the plane of the paper. Now the next case is uniform field perpendicular and inward to the plane of paper, and next one is the uniform field perpendicular and outward to the plane of the paper. So over here this cross and this dot shows you the inward or the outward magnetic field, because in so many problems you are going to get the diagram in which either the cross have been given or the dot have been given. So you should know about the meaning of. Now in the very next case I am going to discuss about the magnetic field lines. So what are the magnetic field lines? So obviously we have just studied about the magnetic field, which is the space around the bar magnet, imaginary space in which we can experience the magnetic force of attraction. Now magnetic field lines are nothing but these are the imaginary lines which gives pictorial representation of the magnetic field inside and around the magnet. Now what are their properties? So first property says that these lines form continuous and closed loop. So this I am going to show you with respect to the diagram only. So over here you can see that there is no line which is breaking, all the lines are continuous and these are also forming the loop. Now how these are forming the loop? Here you can see that always we have studied from the childhood only, from 7th class onwards, that in the bar magnet the magnetic field lines generate from the north pole and they used to terminate at the south pole. So that is why we have shown the direction like this. Now how these are forming the closed loop? So there is a magnetic field lines, or there are the magnetic field lines, which are passing from, you can say, from south to north pole inward to the bar magnet, and this is only due to the dipole moment of the magnetic material which is present inside it. All the atom have its own dipole and the dipole have its dipole moment which is aligned from south to north. So that is why it always forms a closed loop. It generates from north pole outward and terminates at the south pole, and inward it is always from south to north. Now in the very next case I am going to discuss about the tangent to the field line gives done by just plotting the tangent to that particular line. So here I am just assuming a point on this particular here you can see. So over here if I will just make a tangent which is just touching and passing through this, and as the arrow is pointing from north to south, so arrow will be in this direction only. So this will be the direction of magnetic field at this particular point. I'll denote it with respect to the any different color so that it will be clear to you. So at this particular point, if you want to calculate the direction of magnetic field, simply what we have to do is we have to plot a tangent here. Now in the very next case I wish to discuss the third point, that is larger the density of the lines, stronger will be the magnetic field. So as in the just previous slide I have discussed with you that the force of attraction will be more at the poles and it will be you can say less towards the you can say with respect to the magnetic axis. If towards the longitudinal side we want to see, then the force of attraction will be less at this side and it will be more towards the north pole as well as towards the south pole. So over here you can see that the larger the densities of the line, so here you can see the number of magnetic field lines are more at south pole as well as at the north pole, and the number of magnetic field lines at the you can say the longitudinal side, that will be lesser. So in the very next case the fourth point says that these lines do not intersect with another. Now this point is very important point. That means why these are not intersecting. Here also we can see that the no line is intersecting with each other. Over here also we can see that no line is intersecting with each other. There is a reason that two lines are just intersecting with each other. This shows that the magnetic field at a single point magnetic field has its two different direction, which is not at all possible. As in this particular figure you can see that at a particular point, if with respect to these arrow I wish to show you, then in this particular case you can see that at this particular point you can see that the direction of magnetic field lines are same. Similarly at this point if you want to see, then again the direction of magnetic field lines are same. So these lines do not intersect with one another, because for intersection it should have the different direction at a single point, which is not at all possible. Now in the very next slide I am going to discuss with respect to you can say magnetic dipole. So what is magnetic dipole? Dipole means having two poles, and in magnetism chapter we know that there are the two poles which are generally present in the bar magnet or any of the magnet, that is in north pole as well as the south pole. So there will be the dipole moment too. So first of all we are going to define what is magnetic dipole. So magnetic dipole is an arrangement of two unlike magnetic poles of equal pole strength separated by a very small distance. So this I wish to make the diagram so that it will be more clear to you. So here you can take the bar magnet. So this is the bar magnet, and in this particular bar magnet you can take one pole here, another pole here. One is say the north pole, another one is say the south pole, and now these two different or unlike poles having the equal pole strength, that means N is and these two are separated by the equal distance with respect to the center. You can take either from this side or this side or this side, and the total length you can say is 2L. So I hope with respect to the diagram it is clear to you that two unlike poles which are separated by the equal distance from the center and having the same pole strength. So over here QM denotes the pole strength and it is same for N and S, but generally we used to denote it with respect to the plus and minus. So minus indicates the opposite pole strength. So now in the very next case I wish to discuss the very next with respect to the diagram. So here I have shown you the magnetic dipole, in which first I have shown you the, in this particular case I have shown you the electrical dipole, in which I have shown you the two charges separated by the equal distances having the same charge but of opposite nature. So first one is a positive charge shown by the red color and the negative charge which is shown by the blue color, and it has its dipole moment P, which is denoted by this particular arrow, and it is always from negative to positive. But in case of bar magnet you can see that this is the bar magnet which has the two poles and at S, and it has the dipole moment from S to N. So generally S is considered as the negative pole and the S is generally considered as the positive pole having the positive pole strength. Now next case is the magnetic dipole moment. So what is magnetic dipole moment? So magnetic dipole moment is nothing but the product of the distance to the pole strength multiplied with the distance of separation between the two pole, which is 2L, as I have just shown you in the diagram that I have made for the bar magnet, in which I have shown that the distance between the two poles, unlike poles, is 2L. Total distance is 2L. So it is generally denoted by mu. So here in this particular equation you can see that mu, that is a vector quantity which is equal to m into 2L, where L shows the distance between the two dipoles, but over here L is a vector quantity because the direction of mu is fixed from S to N. So that is why L is denoted by the vector. Now its SI unit is joule per Tesla, or its SI unit is, you can say, ampere per meter square, and its direction is always from south pole to north pole. So in the very next slide I am going to discuss about the current loop as a magnetic dipole and its magnetic moment. So as in the fourth chapter we have studied about the current carrying loop, in which we have calculated the strength of magnetic field. Now as we already know that if there is a circular coil, it is going to have some magnetic field. Now we want to show that that particular magnetic field has the two dipoles, and how the dipole we can calculate and direction of magnetic field we can calculate, and how we can get the dipole moment of that particular current carrying loop, that we are going to discuss in this particular slide. Now in this particular case we are assuming that a current carrying loop behaves as a magnetic dipole. If we look at the upper face of the loop and the current is flowing in anti-clockwise direction, the north pole at its the, you can say, bottom face. But in this particular case you can see that the polarity of the pole which is generated due to this current carrying loop is changing depending upon the direction of current, that we can calculate with the help of right hand thumb rule. So, or you can say apply the axial vector and try to get the direction of the magnetic field. You can get the direction of magnetic field, and always inside the coil the direction of magnetic field with respect to the dipole moment, if you want to calculate, it is always from S to N. Now in the next case I am showing you the diagram. In this particular diagram you can see that there is a area A. This current carrying loop has the area A, and over here the dipole moment have been given by mu is equal to I into A, and the current is flowing in the anti-clockwise direction, as you can see in the diagram. Over here I am also showing you that there is a north pole on the upper face and there is a south pole at the bottom face, which is generated due to the magnetic field which is generated due to this current carrying loop, and in which the current is flowing in the anti-clockwise direction. As in this particular theory I have already explained you that when the current is flowing in the anti-clockwise direction, then it has the north polarity at its upper face. So at the upper face I have shown you the north polarity, at the bottom face I have shown you the south polarity. Now over here the magnetic dipole moment of a current carrying loop is given by, now as over here we have the area and the current due to which the magnetic field strength have been generated. So mu have been given by area into the current which is flowing in the this particular loop. And mu is also a vector quantity, as we know that dipole moment is a vector quantity. And if such type of a circular loop have the n number of turns, then in that particular case you can say mu is given by NIA, where n is the number of turns in the coil. Now here I is the current and A is the cross sectional area, as already I have told you. So this is a, you can say, current loop as a magnetic dipole and its dipole moment. So now we are clear with the concept that the circular loop in which the current is flowing is going to have its magnetic dipole, and it is also going to have its magnetic dipole moment. Now in the very next slide I am going to discuss about the magnetic dipole moment of an electron. Now I am going to discuss the miniature part with respect to the nucleus and the electron. As we know that electron, if it is flowing, then it is going to have the flow of current, which will be very small with respect to electron if I am talking about. And in a fixed orbit, if this electron is revolving, then obviously it is going to have a current in a circular loop, as just in the previous slide we have discussed. So in this particular case you can see the diagram, and according to the diagram there is an assumption, as you can read from the slide. Electron is revolving around the nucleus, and as denoted here in this particular, near to this nucleus the electron is revolving in a circular path and having the radius r, which is denoted here, and the speed of this electron is v. Now the electron is equivalent to the, you can say, electrical current in a circular loop, as in the previous case just we have discussed. And here I have shown you the mass of the electron considered as a me, and this E charge shows the charge of an electron. Momentum 2. Now in the very next case I am going to discuss about that what will be the value for the dipole moment. So I will be given by E by T, as we know that the current flowing in any of the circuit is simply defined as charge flowing per unit time. So charge over here is the electron and time is considered as T, which is equal to E by 2 pi R by V. Here we have replaced the term T by the total distance upon the velocity, or you can say the speed. So distance in a circular path will be given by 2 pi r, and the speed is nothing but v. Then we have got the term t. So we have replaced this term t in this particular part, and over here you can see that the current we have got in terms of EV and 2 pi r. So it is given as EV by 2 pi r. So this is the formula for the current that we have got. As we know that mu is equal to A into I. So area also we need to calculate over here, and so for area we are going to calculate So if r is the radius, then area of a circle is simply given by pi r square. So area will be the pi r square. Now I am going to just replace this term in the magnetic moment formula. So over here mu l denotes the orbital magnetic moment of an electron. When the electron is revolving in its fixed orbit, it is going to have its orbital you can say magnetic moment, and that moment is denoted by mu l, which is given by I into A. So in this particular formula you can see that mu l is equal to I into A. So simply just substitute the value of I as moment. Now in the very next case I am going to discuss about the Bohr's magneton. So it is the magnetic moment associated with an electron due to its orbital motion in the first orbit of hydrogen atom. Now we are just, you can say, making it more compact with respect to the hydrogen atom, as the hydrogen atom has a single electron and fixed one orbit. So in the first orbit, if we are going to calculate the orbital magnetic moment, which will be called as Bohr magneton. So this magnetic moment is simply given by mu b. So this is mu b. It is also known as the minimum orbital magnetic moment attained by the electron. So it is mu l min, denoted as mu l min, and it is given by Eh by 4 pi me. So here the question arises, how we have got this expression. So this expression we have got with respect to the Bohr's quantization condition, in which we can get the linear momentum angular momentum L in terms of, you can say, nh by 2 pi. So simply just by doing the calculation we are going to get this particular formula. Here I have just given you the formula only. So mu b is given by Eh by 4 pi me. Now in the next case I am going to discuss about the spinning moment. So as we know that the electron used to revolve in a fixed orbit, as well as it is showing the spinning moment with respect to its mean position. So the magnetic moment possessed by an electron due to its spinning motion, that is mu s, which is equal to minus E by me into s. So mu s shows you the is the mass of the electron, and s shows the angular momentum with respect to its spinning motion, or simply you can say spin angular momentum. So up to here we have discussed about the basic, that is the introduction to the magnetism chapter, as well as we have discussed about the properties of the bar magnet, as well as the properties of the magnetic field lines, and in the very next case we have discussed about the magnetic dipole and magnetic dipole moments basic and their definition. After that we have discussed about the current carrying loop having the magnetic dipole and magnetic dipole moment, and in this particular topic we have discussed about the magnetic dipole moment of an electron. Now in the second part of video I am going to discuss about the earth magnetism. So in this particular case I am winding up with the video. So thank you so much.